Mechanics Machinery course lecture on acceleration analysis. Here we go. We've got this in our notes. This section is going to look at, well, the acceleration analysis of mechanisms. We will look at analytical techniques. We will not look at classical techniques. They're out there. Classical techniques were really prior to having computational tools, computers. We'll be just looking at analytical techniques. I've just got it here to remind you of that. It is interesting. You could do classical techniques simply with geometry, graphical tools, but we are going to focus on writing equations. These equations, of course, are the second derivative with respect to a fixed frame of our position. That gives us the acceleration. That's the gateway to dynamics, so it's very important. And then we solve those equations, computationally. So it's a very nice, straightforward process. Okay. So let's start looking at an overview of the acceleration. A few important aspects associated with the acceleration analysis. Well, it's in the process of kinematics. We started off with position. We took one derivative with respect to time. That gave us velocity. We took a second derivative with respect to time. That gave us acceleration. That's very useful. That's what we're after here. So that'd be the second derivative of position. Acceleration, like I said, is the gateway to dynamics through Newton's second law, F equals ma. Just call that Newton's second law. And as a quick reminder, to apply it to Newton's second law, we have to take that derivative of acceleration with respect to a fixed frame. But acceleration is kinematics. It is describing motion. It's describing the second derivative of motion. And usually it's the kind of the key stopping point, although we can keep going. Just a quick fun aside, if you want to keep going, take another derivative. We call that jerk. And I was just talking with a few of my robotic geek friends, and we were talking. The next derivative, I think, is often called snap, followed by, you guessed it, crackle, and then pop. And I'm not sure who describes that, but I knew a guy many years ago that was actually, he was a professor, had a company, and he was actually working for high-end golfers. He was taking high-speed video of their golf swing. He was taking derivatives out here, seventh, sixth, this is second, third, fourth, fifth, sixth. This is the sixth derivative. He was taking out fourth, fifth, sixth, seventh, eighth derivatives of their motion, defining their motions, telling them how to change. They were paying big money to get a better golf swing. I always thought that was pretty amazing. Occasionally done on advanced motor control, but frankly, acceleration and jerk are the two things that are important. Acceleration gives us forces, jerk gives us impulse. I spelled that wrong, impulse. Okay, the types of equations that result when we take acceleration, well, those once again give us linear equations. The equations are linear in the unknown acceleration terms. So that's beautiful. Linear is what we like to hear as engineers. We've got all kinds of tools to solve linear problems. The general approach is straightforward. We get our equations. They're loops and constraints. Should have called them LEs, loop equation and constraint equations. We take our second derivative of those guys to get our acceleration equations. We put, those are vector, typically in vector form for the loops, scalar form for the constraints. We then cast them all into scalar form. So we write them out as X, Y constraint equations. And then finally, we put them into matrix form. We write them as linear equations, write our big equation, our coefficient, capital A matrix times our vector of unknown accelerations equals our right-hand side B. And uses and applications. Well, all kinds of uses. The first one I've already mentioned, it's the gateway to dynamics. So we use it if we're trying to solve for forces. We can find, advanced motion. We can think if the acceleration is defined for a particular motion, we could define that, defines motion. So I think these are probably the two key things that I want to do with those. Okay. So next, looks like we've got a lot of language here. Nice written, a written description of what we just talked about. But I've broken the problem down into these, it looks like these 5 steps. And the first step is to get your position solution. So, you know, the process to get that, we get a schematic. We check our mobility. We get our vector, vector model. And we write our knowns, and finally we get our equations. We will need the velocity terms along the way. So you're going to, not only you're going to, and then you have to solve. I guess you have to solve the position. You are going to have to solve the velocity problem as well. So you're going to have to solve the velocity terms as well as the position terms. You'll need those going into the acceleration, but we've already talked about that. Step 3, we're now going to list our acceleration unknowns. And, you know, this follows the same way. First of all, we say that constants are known. So I'm going to write that down again. Constants are known. And we assume they're known because we could look them up from CAD drawings. We could measure them. So they're always knowns. And also, for what it's worth, a derivative of a constant or a second derivative of a constant, I'll call it C, or I'll just call it constant, is 0. So they're known at the position level, but they just disappear at the velocity or acceleration level. So really looking at things that vary in time. So varying, I'm going to make a new word, varying things. Okay, so that could either be changing angle or changing length. So I'm going to list all the things that have changing angles and changing length. I'll write them down. They'll be like theta 2, and now they're in acceleration. So there'll be theta 2 double dots. I'm using the double dot notation to refer to the second derivative in terms of time. That's a scalar. That's the time rate change of this scalar term. I might have some length changes like R4 double dot. I'm just making up variables, so we'll list all those. Finally, of that list, we'll identify the things that are inputs. I tend to put a little box around them. If it's a 1 degree of freedom system, it's a 1 input, 2 degree of freedom, 2 inputs, and everything left are my unknowns. And with those unknowns, I can go back and look at my equations, make sure they balance, and I solve. Okay, step 4, we get our equations. We take the second derivative of the loop and constraint equations. And then if I have a point that's not on the loop, but I want the acceleration of that point, just like velocity, I'll take a derivative, the second derivative of a chain going from ground out to the point of interest. Very important that you start from ground. Finally, I have linear equations, so I write those out as my linear equations. I'll isolate the unknowns on one side of the equation, knowns on the other, Spanish scalar equations, cast the matrix form, and then I solve in MATLAB, my calculator, Excel, Python, whatever tool you like. So that's the process. All right. So, you know, the key idea here, the additional thing, this is the same process as velocity. The additional thing is derivatives. So we're taking a second derivative. In velocity, we took the first derivative. So let's go and practice that. Let's take a few minutes and practice taking the derivatives. We made a decision in this class. We could use a Cartesian vector notation or a different notation. I suggested a complex polar, and we agreed to use this. So I've got a star and a happy face. We've agreed to use it. We have to be careful. I guess I could put a frowny face. We got to be careful because this works great for 2D, two dimensions. It doesn't work for 3-dimensional problems. This is a 2D class. If you want to go to 3 dimensions, we have to jump back over the Cartesian notation. Not a big difference, but just something to keep in mind. Most of the world, 80–90% of the problems can be approximated as 2D problems. All right, so let's review this. So, you know, our vector we write in this complex polar notation. So our vector is our length times e to the I angle. Our acceleration, and that's a vector, is the second derivative of that vector. Okay, so let's break that down. So let's, you know, I think the easiest way is to take one derivative at a time. So let's say it's going to be the ddt of the ddt of r. Okay, and I'm going to kind of go down. Hopefully I won't run out of room. Well, I'll go right a little bit and then I'll go down. So the ddt of r, we're now well practiced at it. It has 2 terms. The derivative of the first times the second plus the first times the derivative of the second, which is I theta dot. You know what? Let me move my I over. R theta dot I e to the I theta. Okay, we remember that the magnitude is here, and then the angle is here, the direction, excuse me. Now we got to take the first derivative of this term. Okay, so we're going to start watching. Now we've got to, again, apply the product rule over and over. Let's start first on the left. So I've got the derivative of the first, so it's going to give me r double dot times the second, plus the first times the derivative of the second. So that's the theta dot I e to the I theta. Okay, so those are the two terms I get here. Now I've got to go to my second term. Now the second term's got three parts. It's got an r, a theta dot, and an I e to the theta. So let's do each one in turn. So first we get the derivative of the first, which is r dot times, so the derivative of r, which is r dot times theta dot I e to the I theta. So that's the first term. Then I've got an r times the derivative of theta dot. That's, should add up plus there, sorry. R times the derivative of theta dot, which is theta double dot, times the direction I e to the I theta. So far, so good. Now I've got the first times the derivative of the second. So I get an r theta dot. The I is a constant, so I'll just pull that out as well. Times the derivative of e to the I theta. Derivative of e to the theta is theta dot I e to the I theta. Okay. All right, so there we have it. So at the moment, it looks like I have five terms, but we can collapse a little bit, and I'm going to rewrite them in an order. So first we have the r double dot e to the I theta. I'm going to pull this theta double dot term next, if that's okay. No particular reason. There's no particular order, but I'm going to do that. R theta double dot I e to the I theta. So you can see those two terms. That's easy. Now let's look at, let's grab this last term next. Okay, the last term is an r theta dot. And then I got an, excuse me, r theta dot squared, right? R theta dot squared, so two theta dot, times I squared. What is I squared? I squared is -1, so I'm going to put my negative out front, e to the I theta. And then finally, I've got two of these things. I'm going to put a little squiggle under them. Look, I've got two of those, so I'll bring those down. And I know that's going to stay positive, so I'll write them positive right now. Plus 2 r dot theta dot I e to the I theta. Okay, that's a little messy, but that's my acceleration. Ta-da. So four terms that show up. You know, I started off with a vector, just had length and angle. One term, I took one derivative, that gave me two terms. I take a second derivative, that gives me four terms. Kind of think about where to go. Could take more derivatives, but we're stopping here. For fun, I'm going to come back and tell you a little more about those terms. But there, you need to know we have the terms. And then to expand, we've just got to take our cosine and sine. So the x component is going to be the cosine of each of these terms, and the y component is going to be the sine of each of these terms. So an r double dot cosine of the angle, and cosine of the angle is theta, and r double dot sine theta. Second term is r theta double dot times the cosine of the angle. Now the angle is e to the I theta rotated by I. That means rotated by 90. So cosine plus 90, and r theta dot sine theta plus 90. Third term, I've got a negative. So negative magnitude, r theta dot squared times the cosine of theta and the sine of theta. And then the last term, I get plus 2 magnitude. Here's the magnitudes times the angle, cosine of theta rotated by I, or rotated by 90. So theta plus pi halves. And here's the y term, sine theta plus pi halves. Oh, beautiful. So straightforward, so beautiful. Okay, we got this nice little table. So if we want to summarize in the table, our vector r had really just one component, r e to the I theta. The acceleration is the second derivative of this guy. So that's the d squared dt squared of r e to the I theta. And that gave us the terms r double dot e to the I theta. It gave us the r theta double dot I e to the I theta. I'm just writing from above. It gave us the negative r theta dot squared e to the I theta, and finally a plus 2 r dot theta dot I e to the I theta. Add one more row. We got our AX term and our AY term. I'm going to let you expand those out, but you should write those into your notes. So you have an R double dot cosine theta and R double dot sine theta. You should complete these notes. Okay. And then for fun, and I should have put this, maybe I could use my space a little more usefully, but I can name these. This first term, often we call the linear acceleration. The second term, often we call the angular acceleration. And these are the components. This is not the complete acceleration, but this is the acceleration due to the angular part. This third term, I always call Coriolis, centripetal, excuse me. Good old friend, centripetal acceleration. And the fourth one, wait for it, Coriolis, the famed Coriolis acceleration. And you can see them. Linear acceleration is just the rate of change of the vector. Angular acceleration is the rate of the second derivative of the rate of change. The angular is the second derivative, the rate of change of the angular motion. Centripetal is the squared rate of change, so the squared angular velocity times the length. And then the Coriolis is the product of the linear rate change times the angular rate change. You got to have both components. Okay, there you go. Lovely table. Now, let's take a look at that a little bit more. Need to have a little link. Oh, we should watch Fast and Furious 2 here. If I knew how to pause, I'd do it. In Fast and Furious 2, this was really popular a while ago. I don't know if they're still making them. You know, people racing cars in LA. Not such a big thing in Tennessee, but anyhow, I'm looking for a good example. So I think in Fast and Furious 2, maybe some other ones, there's a race and they're running along, and then there's a drawbridge, which is shown here on the left. You can barely see the car in my picture. The car is there. Change the color of my pen so the car is here. Anyhow, they're racing along the drawbridge. So the car is here. It's the drawbridge, kind of pivoting somewhere back here. The drawbridge is rotating. Now, I guess if it's going up, I kind of have a negative acceleration. I'll just call it a theta dot term or an omega. The car has got some linear velocity, r dot, along there. There's some r going out from the center. I'm just going to assume it's a constant offset there. That's my r vector. And if I look at what's going on, I can see that the car has these terms. So I might ask myself, well, what's the acceleration of these guys as they're racing along this bridge, this rotating drawbridge? Well, first of all, I have that linear term. So it's the rate of change of the second derivative, the rate of change of their motion along the bridge. And that's in the direction of that theta. So I come up here, I'm going to have to show this guy. I'm going to get rid of that thing. That guy is going to be in this direction. So it's in the theta direction. This is theta. This is my r double dot e to the I theta. That would look like if I'm looking at the speedometer, it's the rate of change. It's the moving of the speedometer. The moving speedometer. So if it's fixed, that thing is 0. If the speedometer is going up, I'm increasing. That value is positive. If the speedometer is going down, I'm decreasing. All right, second term is the r theta double dot and the I e to the I theta. Well, in this example, because I'm rotating down, I should have inverted this picture so it would go the other way. But in this case, my theta is here. I need to add another 90 to it. So in this example, the center of the car is rotating down. So I get a 90 degrees. So it's a 90 degrees r theta double dot I e to the I theta. This is due to the rate of change of the drawbridge. So here I'm assuming the drawbridge is kind of going down. That's a positive direction. And if it's actually going down at an ever increasing rate, then I get this guy. That's the drawbridge part. Third term is minus r theta dot squared e to the I theta. Oh, I forgot my squared, theta dot squared e to the I theta. Okay, what's its direction? Well, its direction is in the e to the I theta negative. So it's this way, r theta dot squared negative e to the I theta. So it's completely opposing my motion along the the bridge here. Okay. And then the last term is the Coriolis term. And what's its direction? Well, its direction is also I e to the I theta. So if I jump back up here, I've got a second term coming down here, and that one is 2 r dot theta dot I e to the I theta. So it's in the same direction as my theta dot term, double dot term. So those two things add up. They're both in the 90-degree. And that's a combination of the speedometer, the value from the speedometer, and the rate at which the bridge is rotating. Okay. So this is the bridge, the bridge rotating. And this is a combination of speed times bridge rotating. Okay, so I get all these terms. And then I just take the vector sum, add them up. That gives me the total acceleration. Voila, kind of magical, kind of neat. All right, so if you have a hard time thinking about the directions, just think of Fast and Furious. Go watch an episode or two. I don't know if any of it makes sense, but watch an episode or two. Okay, a couple examples. I'm going to try to make this pretty quick, but a couple examples of each of these. Where would you feel linear acceleration? Well, let's say you have a friend that's got a car and they like their car and they drive fast. Oops, that's a pretty bad picture. You ask, hey, I need to go to Walmart. You ask your friend, so they jump in the car. They want to show off their car. No, they're sitting at a stoplight. A stoplight, red, yellow, green, and then the light turns green, and they step on the gas. Okay, so the light turns green. They're spinning out their tires. They are. Notice what's happening. They're going to step on their tires. They're going to have an acceleration in that direction. They're going to have an r double dot e to the I theta because this is their direction. Their theta is that. Oh, and I drew it in the negative direction. I should change my drawing to go the other way. Yeah, it's in the direction they're traveling. I'll try to fix from here. I'll try to make them hold that way. Now, if you were in the car, you would probably say, would you say, oh yeah, you're accelerating, to the left in this drawing. Would you say, oh yeah, I accelerate to the left? You probably wouldn't say that. You probably say something like, I was thrown back into my seat. So like this person might say, oh, I was thrown back in my seat. Maybe you have long hair and you get thrown back in your seat, okay? Well, that seems inconsistent because we said we're accelerating to the left, but you might say, well, I was thrown to the right in this crazy drawing. Well, is that possible? Well, think about what's happening. You're sitting at the stoplight, no acceleration. Your friend slammed on the gas, started spinning the tires. They started accelerating rapidly to the left. You were at a rest state, right? You're not going to all of a sudden start accelerating unless there's a force on you. So you reported being thrown back. That's not what happened. You wanted to stay right there. All of a sudden, the car seat started pushing on you to the left. You felt as if you were pushing back on the car seat to the right. So that's consistent with your perspective, but you weren't being thrown back. You were being accelerated forward by the seat. You felt it by being pushed back. So that's the way to think about these things, okay? Okay. The second one is the angular acceleration. I don't have a good example for that one. I can't think of where you're on some platform that's angularly accelerating and you feel it. I've tried. I'm sure it's out there. Let's go to the third one, centripetal. Let's say you go to the fairgrounds or the fair or the fair or some amusement park and you ride that centripetal. Well, they call it the what do they call that big thing? Like Space Age 2000. I don't know. You stand on the wall, and the thing starts spinning around real fast. Like so, some theta dot term. You're on the wall, and then the floor drops down, and you just stay on the wall, okay? So you just start spinning around and around and around, okay? And you just spin faster and faster. Now, we just said that your acceleration is toward the center. So it's going to be, the vector is going out to you. The r e to the I theta is going, the r e to the I theta is going that way, but the acceleration, the negative r theta dot squared, is going that way. So your acceleration is toward the center. I'm sure you've been on these things. You get in them, they start spinning, everything's fine, spins faster and faster, you're getting pushed up against the wall. The floor drops out, you're hanging on the wall, some crazy people are climbing around. They're gonna die. I don't know why they do it. Your report is you're being thrown out. You're saying I'm being thrown toward the wall, but you're actually accelerating toward the center. If we look at the top, we look at the top of that thing. So it's accelerating this, we've got that velocity. You're out here. You're out here pressed against the wall. You feel like you're being thrown outward, but actually you're accelerating toward the center. And think about that. You kind of keep moving around. You keep moving around. Well, you want to stay on a non-accelerating frame unless there's a force on you. So so basically there's a force pushing you toward the center. Let's think about this for a minute. Let's say you actually climbed up, or one of those crazy people climbed up enough that they got the top and no longer there was a wall. What would they do? They would travel this way. That's the non-accelerating frame. You stay with the centrifuge. I think they call it like the Centrifuge 2000, the Century 2000. Last time I rode one, I think that's what it's called. They're traveling on this non-accelerating frame. You're traveling on this accelerating frame, so you got to be accelerating toward the center. Same thing if you're with your crazy friend in the car. They decide to go around a corner real sharp like this. Let's say you're not buckled up. Let's say the door's not even fastened. You go flying out. You say, I was thrown out of the car. Not at all. You traveled a non-accelerating frame, a straight line. They traveled this accelerating frame, the curved line. There was just no force to keep you on the accelerating frame. So remember, it's easy to think the acceleration is outward. Sometimes people say things like centrifugal force. No, the acceleration is toward the center. The force is toward the center. The force is toward the center. The wall or the seat belt or the car door is pushing on you toward the center to accelerate that way. All right. And then the last one is Coriolis term. And actually, I can think of an example. If you've ever been to Grassmere, there's that big carousel? Carousel with like a horse on it. Trying to draw a little stick horse. Stick horses, they're on it, going around and around and around. Okay, so let's say you're there at the Grassmere hanging out, and you decide to show off to some friends. Maybe you see a girl or a guy you like, and you want to impress them, so you're going to walk. Well, you're on this thing that's rotating with some theta dot. If you decide all of a sudden, I'm going to start walking, let's say you decide to walk this way. So, here's your R vector. You decide to walk in the negative R direction. Well, you can walk either way. I guess I could have gone positive. Let's change that. Let's make our life a little easier. So you're here, there's your R, and you see somebody, you want to impress them, you want to look real cool and walk past them. So you're going to decide to walk outward, R dot. So we said that this term is R dot is a 2 R dot theta dot I e to the I theta. Okay, so there's your theta. Here's theta plus 90. So this says that you are going to feel an acceleration in this direction. Now you're on this rotating path, so you already have some centripetal acceleration toward the center. You've accommodated for that. You can kind of lean a little bit from that. But let's say now you're going to take a big step to go out. There is going to be acceleration going sideways. I don't know if you've done that. Go try it. You're going to feel like you fall over. Definitely stand there for a minute and then just start walking fast. You are going to fall over. The acceleration is going to be that way. You are going to your left in this drawing. You're going to then tumble to your right. Unless there's some force making you accelerate that way, you're going to tumble to your right. You're going to try to travel this way, a non-accelerating path. That is Coriolis acceleration. You can absolutely feel it. It's a big deal. There's a lot of places where it shows up. Okay. Anyhow, that was a quick description of all those terms. We have that actually is going to bring me to the end of this discussion. We've got we've got our loop equation. We have to take the second to get acceleration. We take the second derivative of this guy. So that means we have to get 4 terms for each. So I get an R1 double dot e to the I theta 1 plus all those terms. Plus I get R2. I got to take all 4 terms of this guy. So a lot of work. I say a lot of work. There's some work there, but it's just a standard process. I go through, I expand, and I solve. All right. Thank you for your attention on acceleration. We'll work at example problems in class.